Welcome, everyone. We are at the third Bicentennial Mini-Science from McGill University. We are located on the traditional territory of the Haudenosaunee and the Anishinaabe nations. McGill University respects, understands, and acknowledges these nations as the traditional custodians of the lands and waters on which we meet, on which we work, on which we play, on which we exchange information. Tonight, our speaker will be introduced by the student ambassador, Grace Goebelle.
Hi, so tonight we have the lovely Professor Tomislav Friščić. He is a professor at McGill in the chemistry department. He describes himself as a solid state chemist, and he works primarily with mechanochemistry and solvents. He received his bachelor's in Croatia and has since gone on to the University of Iowa and Cambridge. He has received many awards and fellowships, including the Rutherford Medal in Chemistry, and we're so excited to have him here to talk about the future of chemistry.
Thank you very much, Grace, for this really generous introduction. And it is really a tremendous honor to be invited and have a chance to talk to everybody here online for this special event, the second centenary of McGill University. And before I start talking about the topic of this short seminar on the future of chemistry, I want to highlight just this one picture that I have here, which some of you from McGill University may recognize. It is the old physics building, which is now currently a library. And I think it's a very special building to highlight at McGill for a natural scientist, because this is the physics building in which the famous Ernest Rutherford did his seminal research at the turn of the 19th to 20th century, demonstrating very important facts, the existence of the atomic nucleus, for example, about the structure of the atom. So before I also start, I probably should highlight that the reason I'm here and have a chance to talk about chemistry and talk about the sort of things that my group does is because they're just an excellent group of people. So some of the results, a lot of the results, all of the results I'm going to show to you today are really coming from the work of these really very exciting, very diligent, and just overall fantastic people. Undergraduates, graduate students, postdocs, they're just great. And I'm very grateful for all the contributions they have done. And also, before I continue, I need to warn you, I tried to make this talk more or less fun and more or less on time, but at some point you may decide that listening it is a cardinal mistake. So the topic for today is the future of chemistry. And that's really an interesting topic because when I was asked to talk about it and sort of highlight the work we do, I had to ask myself first, well, what is this future of chemistry? Where is chemistry going in the next 10, 50, 100,000 years? Is the future maybe the amazing, beautiful work that's being done in the UK by the group of Andy Cooper on introducing autonomous, intelligent robots to perform research faster and more efficiently? Is that recent achievement a sign of the future of chemistry? Or maybe the sort of things that we do in the lab, maybe it's developing smart fuels designed to replace the very toxic, nasty materials that are currently being used to propel rockets and satellites in outer space. We are developing materials which are safer and greener, and more importantly, for whom we can actually design at the molecular level their ignition properties. Is that the future of chemistry? Or maybe the future of chemistry lies somewhere else. Maybe with all the popular exoplanet exploration and increased interest in the structure of our planet, maybe the future of chemistry and material science is in finding materials which are going to be inspired by geological finds, either on Earth or maybe on some other planets. That could be the future of chemistry. or maybe the future of chemistry is like something that the Barrett group here is doing, is developing ways to design materials which can be shaped, which can be cut, which can be turned into many forms by simply using visible light. And here I'm showing a video that came from our collaboration with Professor Barrett, especially with the student Tristan Borchers. So is this the future of chemistry? Is this how future looks like? Well, maybe if you ask an excited scientist and a researcher like me, we can talk about all these new opportunities that lay ahead for science, for chemistry, for technology, for our society. But for many people, maybe a more important question from where is chemistry going is where is chemistry today? Where are we now? And for people who are not necessarily professional chemists, the view of chemistry where it is now is something like this. Chemistry does not have a good reputation. And I think that there is many reasons for that, very good reasons. So here are a few newspaper articles highlighting horrible disasters that have been happening in the last 5 or 6 years. Some of them very recently, like the phosphate spill in Florida, Tampa, or maybe I can highlight this event that took place in 2010 in Hungary, a major spill of a so-called toxic red sludge that took place in an aluminum refining plant in Hungary. What happened here is that a highly concentrated alkaline solution was simply spilled from a reservoir, resulting in a huge wave of a really basic water contaminating, essentially destroying life in a couple of rivers, drowning livestock, destroying plant life, killing people. This is what chemistry for many people is today. And if one asks me, well, what is the chemistry of the future? I would like to think about how can we avoid this? No matter what chemistry of the future is, I believe it must be different than this. And in order to try to address this problem, I think it's perfectly fine to maybe go deeper and ask the question, well, what is chemistry itself? What do we think chemistry is? And I'm sure that many of you listening to this have had the chance to take chemistry courses in your schools and universities, and generally this is how people see chemistry. Chemistry, as found in many textbooks, is often reduced to a number of equations, so-called chemical formulas, in which you have something that's called reactants, substances, let's say A and B shown here, and then they convert into a product, let's say C, whatever it may be. And this process of conversion, this is what chemistry is. It is this chemical transformation, which is illustrated by one single arrow. Now, this is a very suitable, systematic way of representing chemical reactions, and I generally think it's very useful. But in many ways, it's also completely wrong. And I want to highlight one aspect on how this representation of chemistry is not wrong, but maybe misleading. Because what this formula here tells us is that we will take A and B, and these are reacting substances, and most substances around us tend to be solids. So we're going to take a substance like this, a solid, and then react it with another solid, mix it, and it's going to turn into something else. If you have taken lab courses in chemistry, if you have seen movies about chemistry, you know that this is not how it works, because what we really do is we take the substance A or B, and we first put it in a large volume of a liquid, which we call a solvent. And then once we have found the correct solvents that will dissolve, solubilize if you want, A and B, then we can mix these solutions together. And now the solutions of A and B mixed together produce the product C, again, in solution. Why am I telling you all this? Well, there is inherently nothing wrong in how this is done, and this is how chemistry very generally, very often is done, except that these solvents are generally not terribly nice substances. Many of them are flammable, some of them are toxic, teratogenic, carcinogenic. They're nasty things that, you know, we can deal with here in a laboratory, but we can't really deal with them so easily in a large industrial setting because they are toxic. So this is how chemistry works. And if you think about, can we do chemistry without having these bad effects of solvents? Well, it turns out that the use of solvents is so ingrained into chemistry. If you look, for example, at classical movie or popular culture representations of chemists like this one here, you know, forget about the frizzy hair and all that stuff, okay? Chemists do that. But what is more important is the representation of all these colorful flasks with different liquids. These are wonderful images. These are very interesting for movies, but they also show how much the existence of chemistry is connected to the use of liquids, of solvents. And you can say, well, maybe this guy here is just exaggerating a little bit. So, well, maybe it's not quite true. Well, you know what? Let's ask the greatest source of information on earth. Let's ask Wikipedia. So what I did this morning, I actually went on Wikipedia and I typed in, what is chemistry? And you know how the Latins used to say, a picture is worth 1,000 words. Don't read this text, look at the picture. The first picture that appears, like little emoji that describe chemistry, it's beakers and flasks full of solvents. It is expected for chemists to be working with solvents and liquids. And what I would like to ask at this point is why? Why? Because if one thinks about how early people used to make things, starting from, you know, creating fire to making medicines, it was very often by grinding things together, by rubbing things together. It's a very ancient discipline. We have this image here of this gentleman or a lady, I'm not sure, making fire by clashing stones together, maybe. That is chemistry. And it is chemistry that did not require any organic or inorganic solvents, no chloroform, no ethanol. Or, for example, these examples of traditional medicines from all parts of the world, including Vedic medicines, that very often involved grinding the substances together in these objects, these mortars and pestles. So ways of transforming substances, which is what chemistry is, without using solvents, have been known for a very long time. So why don't we do it now? And you know, it is perfectly right to ask at this point, well, maybe this professor here is exaggerating. He's showing us all these nice pictures from popular magazines. Maybe he should show us some hard evidence. Well, you know, there's this wonderful book written by a Greek philosopher who lived roughly 2,500 years ago, Theophrastus of Eresos, who wrote a number of books, and one of them is called On Stones, in Latin, De Lapidibus, and I actually don't know classical Greek, so I apologize here. But this is a book that 2,500 years ago really represents a summary of the knowledge of the ancient world about making metals, transforming minerals. You know, if this was written today, I would say this is a textbook of inorganic chemistry. And what Theophrastus describes in there are sometimes chemical processes that do not require any liquids, any solvents for making pigments, dyes, metals. And you can say, how do you know that, Tomislav? Because you don't speak traditional ancient Greek. Well, I know that because on the website of the Ohio State University, you can actually download a PDF copy of this book in Latin translation and also English. And I invite you to read it because it's a really interesting compendium of classical knowledge. But it also tells us that processes to make things without solvents have been known for millennia. So this is something that I'm interested in, and that is, how do we maybe go and re-inspect those old processes? How do we try to maybe step back from the way we are doing chemistry right now and try to maybe simplify it. What do I mean? Here is a graph, a scheme that I'm trying to use to show you a typical chemical reaction in a lab. What you have is a container, which is like a beaker. We call it a beaker, right? Or a flask or something. And inside, we have this blue material. That's a solvent. That's a liquid phase. And inside, you have these orange, these yellow circles, which are essentially our reactants A and B, and so on and so forth. So we wanted them to react, and they're floating around, these molecules, these ions or atoms, they're floating around this solvent. And sometimes we help them interact with each other and transform to the products by putting in some power in the form of heat. You heat things up, things happen faster. Or maybe you add some stirring in it. So you use a overhead stirrer or another device to kind of mix it all faster. So let's try to simplify this story. So on one hand, what we can do is we can try to stop this stirring. Maybe that's not necessary. And you know what? As soon as I start simplifying this process, I'm actually starting to get some interesting benefits, like I'm saving energy. I'm no longer using this power to stir the reaction. And that's good, because I'm using less energy, I'm more energy efficient, and I'm essentially lowering my carbon footprint. And you know what? That's important. And what else can I do? Well, maybe some of the chemical reactions, and there has been tremendous activity in that area over the last many decades, can go without the use of heat. Now I'm really not using much energy at all. I'm really efficient. But I'm going to go here to an extreme. I'm going to say, why don't we get rid of that solvent? And now when you look at this scheme I got here, you know, that looks like how people represent gases in textbooks. So that's not what we want. These molecules that are now on their own, they're not going to be just floating in air. They're going to be attracted to each other through so-called supermolecular forces, so forces that act beyond the molecule, that bring molecules together, atoms together, to form a condensed phase, like this. So now we have transformed our classical reaction, if you remember how it looked like with the beaker, the solvent, and so on, in something very, very different. And if you look at that, this kind of simplification, I'm showing here on one side a high pressure, high temperature reactor called an autoclave. And you know, if you try to simplify this process so that you don't need any of these solvent and high temperatures or pressures, you end up doing chemistry simply by putting things in a dish and letting them react with each other. This is a wonderful simplification, and that simplification, which brings with it a reduction in energy consumption, complete or at least partial loss of a need for solvent, and you know, no solvent, no spills like the ones I described in Hungary, that is really the central aspect of green chemistry. Green chemistry is an area that emerged several decades ago, which is an area of chemical research focused on how do we make the chemical processes in the lab, in teaching, in manufacture, overall, how do we make them safer, cleaner, greener, more environmentally and generally sustainable? So this is a discipline that I would say is terribly important. And it's also a terribly, terribly strong aspect of work overall here at the institution whose 200 years we are celebrating right now, McGill University. And here is just a picture of a few of my colleagues, Professor Matt Harrington, who is a member of our green chemistry cohort of researchers who works in bio-inspired materials. Professor Audrey Moores, a wonderful colleague that we collaborate with a lot on catalysis, nanosystems, solvent-free chemistry. Professor Eric McCalla, who is investigating new ways of storing and delivering energy, new battery materials, and CJ Lee, a globally recognized pioneer in replacing toxic solvents with water, with plain water. So we really care a lot about green chemistry here at McGill. And, you know, it's a tough discipline. You know, sometimes you need to wear your hard hat and, you know, just go against the wall here in green chemistry. The way we do chemistry, this was not just a pun, okay? We actually need to put the hard hat on because we want to do chemistry without solvent. You know, just like that ancient character I'm shown before in a cartoon, you know, who grinds things together to make something new. This is what we want to do. And it's not only us, many groups around the world are doing it. So what are we doing? We are doing something that's called ball milling. And here is a video taken on an iPhone by our former visiting student, Michael Brand, who I believe is now doing a PhD in Liverpool, and our current graduate student, Louis Daw. And here is an image of what we do. We have this reaction vessel, which we call a jar. And inside you have this material, which is our reactants A and B, okay? And you can see there are solids, no solvent here. And here we have one additional component, and that's a ball. Now, this looks like a really very big ball. It's not really very big. It's only 1 centimeter in diameter. And we're now gonna shake this system left and right at a frequency of 30 hertz, which means 30 times changes its direction per second. So let's look at the slow motion movie. And as soon as you start milling, grinding, this is called ball milling, the system changes color. Chemical reaction is taking place, and by the time I finish talking about this, it's done. This reaction, this point is pretty much finished. Very fast, solid-free reaction, and remember, this was a slow motion movie. You know what? I really like this movie. Let's look at it once again. Left and right, and faster, 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 and the product is there. So these reactions induced by mechanical motion, by mechanical impact without solvent, this is called mechanochemistry, and that's something that we find terribly interesting. This is really like a super force, being able to use mechanical force, a little bit like Thor, but you know, not to defend universes and planets, but instead to create molecules and materials in a cleaner, safer way. And let me give you a short story about it, about what kind of molecules and materials you can make. People think that chemists make things which are really complicated, and some of them do. We tend to be very simple. So our target at one point was metals like copper or gold. Everybody loves gold, and not only that they love copper and gold, but these are very useful metals because they're the foundation of all of our electronics, cell phones, computers, satellites, you name it. You need to have these highly conductive, highly robust metals like copper and gold and silver and so on. So what's the story here? Why am I telling you all this? Well, if you look at a schematic, I'm sorry to scare you with all this chemistry here. This is how typically noble metals like gold or platinum or palladium, you know, the elements you also use in car catalysts, this is how they're made. You get them from nature because they're easy to find. They're very stable, so they don't react with other stuff. So you can easily take them out of nature, right? Well, not really. Because they are so stable, so noble, these elements, in order to process them using classical chemistry, you need to dissolve them, and that's tough. And if you look at the schematic I have here, the way, for example, palladium or gold are being converted into other substances which are industrially useful, these are chloro or gold or oropalladates, this is environmental horror. This is the use of nitric acid, concentrated, halogen gas. For those of you who are not chemists, this means chlorine gas or bromine, carbon monoxides, cyanide extraction. This is actually quite tough and demanding chemistry, but not because chemists want to make it tough, but because these elements are very tough to dissolve. These elements are used in chemistry throughout the world. They're fantastic catalysts. And if you want to recycle them, and you should because they're terribly expensive and valuable, the only way to dissolve them and bring them back into processing is by using terribly aggressive liquids like this one called royal water, aqua regia, which is a mixture of concentrated nitric and hydrochloric acids. Not nice stuff, but it's still used not only in laboratories, but also in the manufacture of the elements themselves. There are processes that use hundreds of liters of hot aqua regia on a regular basis. So how do we deal with this? So our student, Louis Daw, decided that maybe we could use solid state mechanochemistry to deal with this. And he said, why don't I simply take the metals like palladium or gold here and convert them into the same substances that the industry is using in processing, but avoid aqua regia. What he did, he decided to use these three little circles. And these three three little circles are a proposed, I'd like to call it intergalactic symbol for mechanochemistry, ball milling things together, which was introduced actually 5 years ago only by the group of Team Hanusa at Vanderbilt University. And Louis decided to explore how he can perform this transformation from a metal to something that's industrially important, so it could be used as a part of the industrial process, but without having to use solvents. And his chemistry worked beautifully. These are pictures of those milling jars, but they used to contain palladium and gold, but what you see right now are these colorful powders. And when you add water to these powders, they completely dissolve. The palladium is gone, the gold is gone. You have converted them to these soluble materials, which are identical to the ones that you would produce from aqua regia, except you did not need that terribly, terribly toxic material. So this is like a brief explanation on what one could use, not just mechanochemistry, but any chemistry without solvents for. And we see it as a way to do, you know what, to do everything, to do this green chemistry, to discover new molecules, to discover new chemical reactions. For us, mechanochemistry is not only cleaner and greener, it's also a way to transfer chemistry into a completely new environment. So, wow, I'm excited. Who cares about this? Well, you know what? It turns out that a lot of people care. For example, pharmaceutical industries are very keen to find ways to make drugs, medicines, without having to use all these toxic solvents needed in chemical manufacture. And here is an overview from a paper we published some years ago on all the drug molecules at that point that have been somehow modified or actually even made through solvent-free processes. And this is really an emergent area. We call it medicinal mechanochemistry. And our small contribution to that was a few years ago, was developing a solvent-free route, which was actually shorter and not only solvent-free, to make sulfonyl ureas, molecules which are known anti-diabetic drugs. So one can actually make real drugs, we call them active pharmaceutical ingredients, using this non-conventional, but really quite ancient solvent-free chemistry. And we are obviously not alone. There is a huge community out there. And one of the members of the community is Professor Evelina Colacino from the University of Montpellier in France, with whom we have taken this synthesis of these anti-diabetic drugs, and she really turned it into a teaching laboratory for students. So by developing an exercise in which students get access not only to the classical dissolve A, dissolve B, but to this different solvent-free chemistry, we can help students, as she puts it, think chemistry, but differently. And what we want to do is we want to simply take these solvents from chemical textbook and just forget about them. We don't need them. We can do so much more without solvents, I would say. And mechanochemistry, turns out, is not only of interest to us and in a few groups, and the International Union for Pure Applied Chemistry, IUPAC, has a couple of years ago placed mechanochemistry among the top 10 chemical innovations that could change our world. The Europe has seen a few years ago the establishment of the European Cost Action Project, which, by the way, is coordinated by Evelina Colacino and Lucia Maini, dedicated to mechanochemistry and industry. And this project brings together, I believe, 40 or 50 research groups in Europe, outside Europe, from academia, from industry, to try to develop this new chemistry. The North America has only a few years ago seen the establishment of the National Science Foundation, NSF, Center for the Mechanical Control of Chemistry, which is, again, focusing on the use of mechanochemistry and similar processes to make things. So IUPAC may suggest that mechanochemistry could change the world, and I would agree with them, because mechanochemistry, by allowing us to think about chemistry without solvents, allows us to think about transforming tough materials, feedstocks, rocks, ores, minerals, recycled plastics, to transform them in a simpler, cleaner way through the solid state directly into new, useful, value-added products. And here are some examples of mechanochemistry that we've been working on here with wonderful colleagues at McGill University. After all, this is the second centenary of McGill. For example, with Professor Masad Dama, who is an expert in DNA and RNA therapeutics, we actually developed at this point a patented technology for solvent-free synthesis of DNA and RNA fragments. So something terribly interesting, and something that on one hand kind of clashes with the classical idea that, you know, molecules of life must form in a soup, primordial soup. Here it's solvent-free, but maybe more importantly, this sort of technology shows a way how maybe at some point we could reduce the consumption of organic solvents and therefore the production of toxic waste in the manufacture of these types of therapeutics by 1,000 or actually even 10,000 times. Together with a enzymology leading group led by Professor Auclair, we have worked to actually use enzymes to break down organic polymers, biomass, cellulose, lignin, components of wood mass, and actually convert them using enzymes into simple small components like sugars, which could then maybe be turned into biofuels or into maybe feedstocks, not sure. But I know that one can take this mechanoenzymatic process and use it on real biomass, on waste biomass, and convert it into valuable small organic molecules for chemical industry or other products. And you know, this is as exciting as it is. There is even a more interesting goal for us out there, and we are currently working with Professor Auclair on that. It's plastics. We are in the middle of a huge plastic pollution problem, and the results we have currently, and some of them have appeared online as a preprint, show that one can actually use again enzymes, again without solvents, to break down plastics into its starting components. So if you ask me, this mechanochemistry really is very, very powerful. I like to think about it as chemistry 2.0, a different way to think and to do chemistry. It actually became so exciting to some of our students that they decided they don't want to follow an academic path. So one of our students decided to start a spin-off company making equipment designed for mechanochemistry. And here is an example of this. And this is kind of shameless promotion, but I really need to show this to you. We've been working together with them on actually trying to see how we can make chemicals faster. And here is a recent device they have developed, which we are looking into, that we believe could be used to produce chemical products, new materials in very, very short times. We are thinking about, you know, the kind of Star Trek replicator. You know, you press the button and 60 seconds after that, your product is there. So this is something that we think that this new technology could actually enable. Another student from our team has started up a company dedicated not to mechanochemistry, but to green materials, specifically greener rocket fuels, company called Axinam. And this student, actually, I must mention, is Christina Motillo, and she is actually the winner a few years ago of the really best thesis in chemistry in Canada world. And here I really need to highlight that a lot of work that I presented to you, a lot of ideas are obviously not coming, you know, from me or just from me, but really through the work of these very enthusiastic, very dynamic students. So when I talked about this for a while, I'm really not sure what the future of chemistry is. Maybe it is robots, maybe it's clean fuels, maybe it must be green chemistry, but maybe there's something even more fundamental about the future of chemistry. I would say that the future of chemistry lies in people like colleagues we have here, like Professor Sleeman or Professor Lumb, people who get awarded for their achievements and dedication to developing new concepts, new technologies, greener chemistry. It's not only colleagues and professors, but people who lead our institutions, people like our chair, Dima Perepichka, and all of our support staff who are wonderful people. And you know, people who really maintain this university, people like our building manager, Jean-Marc, or the cleaners, the janitors, they are really the future. They are ensuring the future to happen by helping us all go forward. And not only when things are good, but also during a pandemic. They are wonderful people. They are support staff in more than one way. And finally, really, the future lies in these amazing students, like Christina, like a number of them here in the group, and in other groups at McGill University, who are very productive, very interested, terribly smart, not only times that are good, but also in the times we need to wear a mask and work under special conditions. And at this point, maybe I should not, but I would like to express my huge pride of an amazing research group that I have a chance to work with. And you know, yesterday I was walking home. We can do that now since we don't need to wear masks in public anymore. And I actually bumped into our principal, Suzanne Fortier, surprisingly about the same time that the McGill bus was passing by. And we both agreed on one thing, and that is that better times must lie ahead, and that we have just went over a huge hurdle, and let's look positive and let's be constructive about the future. So with this, I would like to thank you all for listening, and I would also like to just repeat that what we are doing here for this second centenary, we're not only talking about the future and opportunities, we're also celebrating our university, McGill University. So with this, I would like to thank you very much.
Thank you, Tomislav. Professor Friščić, that was an amazing and enlightening presentation. We are gifting you officially, and I hope you can share this with your team. We have a few things that will be coming to your lab. They are things that I hope you enjoy. They are things from the Red Path Museum. One is a kids activity book, but you can still learn from it. Doesn't matter what age you are. Another is this wonderful book, also from the museum, Treasures from the Earth, all the mineral galleries, almost every mineral on display in the museum we've highlighted, and there's a bit of chemistry in here as well. So I think
wonderful. But before we continue, I would just like to say that, you know, talking about better times laying ahead, I would like to thank you, not only myself, but also with the entire group of wonderful people who come here very often, sometimes every day, and never minding how bad things were, they never give up. Thank you so much. And, you know, it's going to get better.
You're right, but I will send you a mask just in case. We do have a mask. McGill Outreach has produced these masks. You might as well have it. You might have to save it as an artifact, give it to your kids, your grandkids. Keep it in the lab. And the last thing that will come in your thank you package is this beautiful, it's a stereoscopic postcard. So you'll take it out of the wrapping, you'll enlarge it, and when you look through it, you will see this dinosaur in 3D. And the museum's not open, but this is a good way to enjoy a little visit.
You have many more of those because we got more people here. Okay?
Oh, good.
We want more. Bring them on. Let me introduce you,
Please.
Dr. Thomas O'Ray, our member who just joined hardly 6 or 7 months ago in the middle of the pandemic. Younger, our terribly talented undergraduate student who came to work with us despite all the troubles of the pandemic. Dr. Dylan Shields, who joined us from Cincinnati. Again, he made his way to McGill across the border during the pandemic. Joe Merritt, probably one of the most talented graduate students I ever worked with. Well, besides Cameron, you're great. So we got many more people here, and we are very, very grateful, not only for this opportunity, but for the fact that the time is right to keep working towards green chemistry again.
I'm glad everybody's there because Grace has gotten a lot of questions while you were giving your talk on McGill's YouTube channel. Quite a few questions have come in. I know, Tomislav, you're not supposed to take the masks off unless you're alone in a room. So maybe this is the cue where all your wonderful team has to leave you, so you can safely answer the questions. Thank you very much, though. That was it was great to see them all there with you. Grace, would you like to go ahead with some of these questions?
Yes, of course. So some of these questions were pre-submitted to us. The first question I have for you, Doctor, is which of the chemical breakdowns takes the longest and is the most sustainable in your mechanochemistry enzyme world?
Oh, so in mechanochemistry, which breakdown takes the longest? You know, that is a really interesting question to think about. See, if you grind things, we think about grinding things to pieces. You know, whenever you break a material, you break chemical bonds. So in principle, breaking things down doesn't take too long. But what we do very often is we try to accelerate the process and actually cheat a little bit, add reagents, traces, catalysts that help things break down. You know, most things that we work on, they can be broken down within, you know, 10 minutes to an hour or so. But, you know, I find that polymers, especially artificial plastics, are pretty tough to work with. And we still haven't solved that problem. They don't break down so easily. They don't break down quickly at all. Other substances that also don't break down are very, very stable substances, which are rocks. They're actually rocks, silicates, materials. For breaking them down, you need to put in a lot of energy. And while in principle, we could break them down by harshly grinding them and putting in a lot of force and energy, we refuse to do that. We are still working on finding chemical tricks that would allow us to break down inorganic, mineral-like substances. And you can say maybe that's not important. And I'd say, well, it is actually quite important because most of our natural feedstocks, inorganic ones, are minerals and rocks. And there is so much energy, there is so much harsh chemistry invested into breaking down, you know, the ores that were used to make the iron from which, you know, your forks and knives or keys are made. So this is something that we are still challenged with. Maybe the answer to the question is not so much it's taking a lot to break them down, but it's taking a lot to break them down in a way that is not environmentally and energetically terrifying. But yeah, stable substances, silicates, organic polymers, those are still wonderful challenges that people want to address. The sooner the better.
Yes, thank you for that. Speaking of plastics, the next question is, how long will it take to break down all the plastic in the world's ocean?
That's a tremendous question. You know, you could answer it with a sub-question. Does that take into account all the plastics that we continue putting in the ocean? You know, it's not going to happen in 5 years. It's not going to happen in 20 years. Maybe 50 years is a good number, maybe a century. I would prefer not to give a number to it because it's a major challenge. And the first thing that one needs when trying to clean up a place, and I'm talking now about an ocean, is stop putting pollution in there. And we haven't even stopped that. So let's be optimistic and hope for 50 years. I would love to be alive when it's done.
Hopefully. Another question we have is, where do you get the financing for all of your research?
Excuse me?
Where do you get the financing for your research?
The what?
Financing.
Finance, oh, the most important factor. You know, we get a lot of financial support from the Canadian government, from our ministry, from NSERC. But at the same time, we also get, and I'm very proud to say that, a lot of support from industries. We get phone calls from industries saying, hey, you and your group, you're doing this green solvent-free chemistry. Can you help us? We have this big process and we would like to remove toxic chemicals from it, toxic solvents. We'd like to be more energy efficient. Can you help us? So right now, probably around half of our finance comes from actually industrial sponsors, from companies that call up and say, can you please help us solve this problem? And I'm hoping that it's going to get even better than that. Not because we want more money, but because it's a sign that industries are very actively looking for greener solutions to manufacture. And when I say industries, I mean industries that deal with petrochemicals, industries that deal with fuel cells, so hydrogen as a source of energy, companies that work with metals and mining, food companies, companies that make pharmaceutical products. It's a very broad area of interest, and I think overall it's a really good sign.
All right, perfect. Thank you very much. I believe that is all of our questions.
Oh, well, thank you very much. I'm really happy to have the chance to talk to you and to talk to everybody else who may be joining, either today or maybe in the future.
There will be joiners. This talk is preserved on the McGill YouTube channel. Next month, excuse me, in about a month's time, July 8th, Thursday night, we will have the 4th mini-science presentation. It is by Graham McDonald from Geography, and the title of his presentation, The Future of Food, Agriculture, and Trade. Ask your questions ahead of time. You'll find it, the link to the Zoom. You'll find the place where you put your questions. Not Redpath Museum, excuse me. Mini-Science McGill. Google that and it'll pop right up. July 8th, 6 o'clock. See you then. Bye, everyone.
Goodbye. Thank you very much. Have a great Thursday and happy Friday tomorrow.